Welcome back, ladies and gentlemen. Here we are, the last piece of solutions, dilutions. Ocean, we're going to run into that so much in this unit, aren't we? A concentrated solution has a lot more solute compared to solvent. A dilute solution has very little solute compared to solvent. We talked about this already. But concentration and dilute are relative terms. For example, I've got three solutions, A, B, and C here. 500 grams of sugar in 100 mils of water, 100 grams of sugar in 100 mils of water, 1 gram of sugar in 1 mils of water. Solution A is concentrated, since it has the largest amount of solute compared to solvent. I think we can all agree on that. This is the one that all the kids want to drink. Solution C is dilute, because it has a small amount of solute compared to solvent. It's only got 1 gram. Solution B is dilute compared to solution A because there's less solute, but it's concentrated compared to solution C because it's got more solute than solution C. Right? This one's got lots, this one's got almost none, this one's in the middle, which means that it's a lot compared to this guy, but it's very little compared to this guy. So, what's the dilution? How do we make them? Well, a solution can be made less concentrated by adding more solvent. Brilliant, right? If I've got lots of solute, lots of sugar inside of my flask, inside of my container, if I add more water, there's less sugar compared to the amount of water. The amount of sugar stays the same, technically, but there's now more water, so it's more dilute. Okay, so we just need to add more water. Problem solved. The number of moles of solute do not change when we dilute them. We just sort of spread them out more. That's all. The number of moles of solute before dilution equals the number of moles of solute after dilution. During a dilution, the only thing that changes is the amount of solvent, specifically its volume. So, how do we do this? Well, it turns out that we do it with math. Yes, we could just take any old thing and just like pour more water in, but if we want to be real careful about it, we got to do some calculations. There's my calculation. It's a ratio calculation. Remember, the original calculation for concentration was C equals N over V. Now, with a bit of algebra, I can multiply both sides by V, cancel out those, and I get V times C equals N. So what I'm saying is the number of moles that I start with and the number of moles that I end with are the same. But if the number of moles are the same, how am I changing the concentration? I'm changing the amount of solvent, the volumes involved. So I'm keeping the same number of moles from start to end, right? It's not like I'm magically making more sugar appear just because I'm adding more water. That doesn't work. So that's how this equation works. It's sort of very similar to the gas unit where we had the various relationships between the different gas laws, right? When we did stuff like immediately blanking P1 V1 equals P2 V2. Remember that one? Right? And it was all related to a ratio. Same thing's going on here. Okay? The only difference is, unlike with the gas law, there's stuff you can physically do. What? Is Mr. C going to have to pull out props again? Before the dilution? After the dilution. Very complicated, very technical. So, we will be going to create a dilute solution of 0.1 molar copper 2 sulfate in a 50 milliliters of water from a starting solution of 0.5. Yeah, we made that last time. Wonderful. So, I have here a very small volumetric flask. It's a 50 milliliter flask. So we are going to use it to dilute, and we're going to dilute to 0.1. Right? This is 0.5, so we're going to dilute by a factor of 5. It should become 5 times less than what I see here. Now again, I can't change the number of moles of copper 2 sulfate in here, right? I can't reach in and pull them out. So the only way I can change the concentration is by adding more water compared to the amount of solute, the copper 2. Now I can't do that in here because this thing only goes up to this line. So I got to do it somewhere else. So in comes the little one. All right, step by step, what do we do? First step, calculate the amount of volume that we need to extract from the starting solution. How much of this do I have to take out? I don't take all of it, because if I pour all of this in here, it's going to overflow. I need to take a specific amount out of here. Why? Because I want to get a specific amount of moles in here, right? The moles in my final solvent are going to be very straightforward, right? We can calculate it immediately. Look, 0.1, 50 mils. There's a set number of moles that have to go in here. So I have to pull that many moles out of here and put them in here. That's the number of moles I expect to see in the smaller flask, right? That's what I said on the previous slide. Moles are the same. So how many moles do I take out to put in here? Then, to change the concentration, I just add a bunch of water. The moles stay the same. Whatever I take out is going to go in here. Now, when I say that, I do not mean number of moles in this giant bottle are the same as the number of moles in this tiny bottle. That's not what I'm saying. What I'm saying is however many moles I take out of here is what I'm going to put in here. Okay? That's the tricky part. Everyone always gets that part confused. Here's our equation, very straightforward. We start filling in our numbers. 0.5 is what we're starting with, but how much am I taking out? I don't know, but I can figure it out. 0.1 molar is what I want to make, and 0.05 liters is how much I'm going to have in the end. So I take those two, multiply them together. At the end, what I'm going to learn is that I'm trying to get 0.01 liters pulled out of here, and that will give me enough moles. How many moles? Well, let's really quickly figure that out, because that's a useful thing for us to be able to compare. So I pull out my trusty calculator, in this case my cell phone, 0.5 times 0.05, and that's going to be 0.005 moles. So over here is going to be 0.005 moles equals 0.5 molarity, moles per liter. So how many liters do I need, right? That's what I'm trying to do here in terms of the math, and there's the answer, 0.1 liters. So what I'm saying is if I take out 0.1 liters, which is about 10 milliliters. If I take 10 milliliters out of here and put it in here, I will have transferred all of the moles that I need to make this solution. There's extra moles left over, and that's fine. They can go sit over there. I don't care. I just need a certain number of moles in here. How many moles? That many moles. How do I know that? From this calculation. Okay? Hopefully that makes sense. So, how am I going to get out of here? Unless it's going to pour. I can't do that. Do I have another even smaller volumetric flask where I can measure out 10? No, not really. The method we're going to use to extract it is called a pipette. And a pipette, they come in a variety of forms. Here's one. The one we're going to use is this guy here. This is called a volumetric pipette. It is carefully marked from 10 to 0 here, so we can add a set amount of liquid inside. And hopefully it'll go right in there. The bulb here, of course, will be used in order to provide suction. In the really old days, people used to use their mouth. Do not recommend. Here we go. We take the lid off. We put it in. We depress, squeeze. Now it will suck rather than blow. Stick it in. Oh, so what happened there is I got an air bubble. And then I just spilled some all over the place. Try that again, this time with less being silly. Get it nice and deep inside. See, I made sure to go in more. Can you see it? There you go. So the pipette tip is very deep inside. That way I'm not going to get air by accident. Okay. Now, if I let go now, it's going to keep sucking stuff up, which is bad because it'll fill the inside of the bulb. So I don't want it to do that. So I'm going to press the tip all the way to the ground. And now I'm going to remove the bulb very gently. And because I'm pressing the tip to the ground, it's hard for the liquid to spill back out again. So it's kind of trapped. Now, if you look, I'm above 10. So I kind of wanted to get it to 10. So you see I'm holding this, and then I just sort of slowly let a little bit out until I am, of course, measuring to the bottom of the meniscus. So there we go. Make sure I don't bring any droplets. This thing has done its duty. Now, this from 10 to 0, I put in here, and this will give me all the moles that I need. Okay, I'll raise it up a bit so you guys can see. Now let it go. I want to make sure I stop it when it hits 10. Some pipettes you stop, some you don't. This one is a stop one. So I put my finger on it, see, and I slowed it down now so I can do it drip by drip by drip. There we go. Get the last little drop. The rest I'll put back in here. And just put it all away. Awesome. So now we have our 10 liters in here. 10 milliliters. Yeah, 10 liters. This is 10 liters. 10 milliliters. Now, just like last time, we fill it to the line. Just like last time, I've got myself something to do that with. Now I got to be careful. Get the line in sight. I'll hold it up so you can see. You normally shouldn't do this. Normally you should always keep it on the table, but I'm going to cheat. And by cheat, I mean do a bad job. The things I do so you guys can see. Drip, 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 drip. That should do it. We're nicely on the line. Now, of course, we invert, get out some parafilm, stretch it out, put it on, wrap it around, and invert. The mixing this time is going to be a lot easier, of course. There's nothing to dissolve. It's already dissolved, and we're done. May as well leave the lid on. And there we go. We have now made a dilute solution. How can we tell? Well, look. There's the one I just made. There's the one I started with. Let me hold them like this so you can see more easily. That's a bit of a difference, right? That's noticeable. This one here, right, has 5 times less moles than this one. Right? Again, this one has less moles, period, right? We calculated how many moles there are in here. 0.001, was it? This one has way more moles in it. But this one here has less moles per volume than this one. If I were to pour out the same amount as each of these, right? If both of these were made to be 50, if I poured only 50 out, and we compared them, they'd look completely the same. They'd compare the same. They'd look different because they both have different concentrations of moles. Either way, there we go. We have successfully created 2 different solutions. This one is a dilution of the original. Can I ever put it back to this? No. Once it's got in here, I cannot separate it out. Well, that's not totally true. I could evaporate the water, but as we know, because of boiling point elevation, that would be tricky. But at this point, we have managed to make a dilution. Remember, the number of moles from here that I took out is the same as the number of moles that are in here. Right? This container has more moles overall, but I extracted a certain number of moles and I put it in here. That's how I made the dilution. The rest of it was just making the concentrations line up. All right. I think I've labored the point enough. There it is. You can clearly see the difference. We've already done the whole fill and rotate and all that and check the meniscus. That's it. There's now some more examples that you can do. Calculate the final concentration when 75 milliliters of water is added to 25 milliliters in an 8 molar hydrochloric acid solution. You have the answers already. Do them. Do them all. Do the practice. Because we're done. That's the end of this unit, which means I will see you guys next time.